Hello everyone. Welcome back to Information Arc. Today we have an exciting topic that's been generating a lot of buzz lately: quantum computing versus classical computing. Have you ever wondered what sets these two paradigms apart and how they're shaping the future of technology? Well, you're in the right place. Stick around as we dive deep into the world of quantum and classical computing, exploring their differences, strengths, and potential impact on our digital landscape. Let's start with the basics. Classical computing, the foundation of our current digital era, relies on bits. These bits, represented as 0s and 1s, form the basis of all classical computations. Classical computers use logic gates and circuits to process information, executing instructions sequentially. In a classical computer, data is processed linearly, making it excellent for tasks such as word processing, calculations, and most of the applications we use daily. However, as we've pushed the boundaries of classical computing, certain challenges have emerged, especially when dealing with complex problems like optimization or factoring large numbers. Now, enter the fascinating world of quantum computing. Instead of bits, quantum computers use qubits. Unlike classical bits, qubits can exist in multiple states simultaneously thanks to the principles of superposition and entanglement. This unique characteristic enables quantum computers to perform complex calculations at an unprecedented speed. Quantum gates manipulate qubits, and quantum algorithms can process information in parallel, making them potentially powerful for specific tasks that would take classical computers an impractical amount of time. Now, let's get down to the nitty-gritty of the differences between quantum and classical computing. Speed. Quantum computers excel at parallel processing, allowing them to solve certain problems exponentially faster than classical computers. Memory. Quantum computers use quantum entanglement to link qubits, providing unique memory capabilities that classical computers can't match. Uncertainty. Quantum mechanics introduces an element of uncertainty, making quantum computing suitable for probabilistic problem solving. Energy efficiency. Quantum computers have the potential to be more energy efficient for specific tasks compared to classical counterparts. As we explore the potential of quantum computing, we're witnessing breakthroughs in fields like cryptography, optimization, and simulation. However, it's essential to address the challenges, such as qubit stability, error correction, and the need for extremely low temperatures in current quantum systems. As we wrap up, it's clear that both quantum and classical computing have their roles in shaping our digital future. Quantum computing holds promise for revolutionizing specific tasks, while classical computing continues to be the backbone of our daily digital interactions. The key is finding the synergy between these two paradigms. And there you have it, the fundamental differences between quantum and classical computing. If you found this video insightful, don't forget to hit that like button, subscribe for more content, and ring the notification bell to stay updated on our latest videos. Share your thoughts in the comments below. Do you think quantum computing will soon surpass classical computing in everyday applications? Until next time, stay with Information Arc. Thank you.